Assalamualaikum, and how are you guys? Before we start lab number 7, let us take a look on the theory behind this lab module. Okay, so the objective for this lab is to simulate, meaning to say using Matlab and Simulink software, to simulate the effect of Kc, tau I, and tau d toward the response of a process. Okay, so here we have liquid level control system, which is a process. Okay, this is a process. And here, this is called instrumentation diagram. Together we have here a controller. Okay, LC is a level controller. We have LT is a level sensor and transmitter. Sensor and transmitter. And then we have a final control element, which is a control valve. So these are the four elements in control system. So here we have a level H as our control variable. We have Q2 as our manipulated variable. And then Q1 as our disturbance variable. Okay. So how this process work? The first one is the level will measure a level inside this tank, which is the value of H measured, and it will send a signal to a controller. So this controller will compare between set point and the measured value. Is there any error or deviation, any difference between the set point and the measured value? So if there's an error, this controller will send a signal. It will send a signal to this. This is called transducer. It converts electric signal into pneumatic signal. Pneumatic signal. Okay. So that this control valve, this is a pneumatic control valve. It will use pneumatic principle to operate. So this controller will send a signal to control valve. Okay, it will send a signal to control valve whether to further open or further close. Okay, let's say our set point is 50 and our measured value is 45. So there is 5 different between the set point and the measured value. So the control valve, the controller will send a signal to control valve. Will send a signal to control valve to further open. When the control valve is further open, the Q2 is increased. When Q2 is increased, the level will also increase. And it goes until the level, the measured value is equal to the set point. Okay, you will learn in detail about this system later on. But in order for you to complete this lab, you need to simulate the effect of Kc, tau I, and tau d, which is the setting for controller. This controller is called PID controller. It has the element of P, proportional, I, integral, D, and derivative. So the value of Kc represents proportional mode, the value of tau I represent integral, the value of d represented by tau d. Okay. So there are a few assumptions here. The first one is the liquid density. Liquid density is a constant. Liquid density and cross-sectional area of the tank is a constant. The rho is a constant and the A is a constant. The flow head relation is a linear, which is for the Q3, meaning to say this flow rate is a constant flow rate. And then given here, the level transmitter, LT, transducer, control valve, level control valve have negligible or fast dynamic. What does it mean by this statement? Okay, later on, later on you will learn about all these four elements: the process, the controller, the sensor, and the control valve. They have their own transfer function. The transfer function for process is known as GP, equal to Kp over tau s plus 1. It is a transfer function. Okay, we have seen how to write a transfer function in Matlab and also in Simulink. We just have to find the block FCN to find a transfer function in Simulink. And then the transfer function for sensor, it would be Km over tau m s plus 1. The transfer function for control valve, it is Kv over tau v s plus 1. We assume everything is a first order transfer function. And also the PID controller. Okay, this controller is known as PID controller. It has its own equation, Kc 1 plus 1 over tau I s plus tau ds. Don't worry, later on you will see all this theory in the class, but I'm explaining it here because I want you to have idea on how this lab module should be done. Okay, and you are given the value of Kp, Km, Kv, and tau. Okay, so what you need to do, go to the result and discussion. You need to develop a simple feedback loop diagram. So you can refer to figure 6.34 and 6.35. Okay. Okay, I forgot to mention that it states here that the level transmitter, transducer, and a control valve have negligible or fast dynamic. It means that the value of tau m, tau v, and also tau ip have negligible dynamic, meaning to say the value is very small and the value is approaching zero. Therefore, the transfer function for Gm will be equal to Km, as the value of tau m, this value of tau m approaching zero. Therefore, Gm is equal to Km. Same goes with the value of Gv is equal to Kv, but not the value of Gp, the transfer function for process. It still have the dynamic behavior, which is Kp, okay, tau s plus 1. Okay, you are given the value of Kp here and the value of tau here. Okay, so let's move to the okay. So what you need to do is you have to develop a feedback control loop block diagram. You can refer to figure 6.34 and 6.35. Okay. Okay, let's go to figures 6.34 and 6.35. Okay. So take a look on 6.35. So you have to construct the same block diagram as this figure. So you have to drag the step PID controller, transfer function, another step, and then mat operation. But for the control valve and the transmitter, you just have to find a block named gain. Okay. So what's this? This is called feedback loop, and this is in Simulink. So in real, theoretically, this is the feedback loop. This is a general feedback loop block diagram. You're going to learn with me later on in chapter 11, whereby the controller, the controller, the control valve, the process, the sensor is connected to each other by feedback loop. Okay, this is the arrangement for feedback loop. Okay, this is an arrangement for feedback loop, and each of the element having its own transfer function. Okay, so you have to understand that this is the 4 element in control system. Okay, there's 4 element, and each of these element have their own transfer function. Okay, the process is represented by GP, the control valve is represented by GV, the controller is GC, and the sensor and transmitter. Sensor and transmitter always came together, is represented by GM. Okay, and then you will learn about transfer function. There are first order and second order. Okay, in this case, we assume everything is a first order. Therefore, for GP, we should have Kp over tau S plus 1. Okay, so Gm is equal to Km only, because it's already mentioned that tau m have very fast dynamic, which is very small. It can be negligible. It's equal to 0. Okay, let's see how we construct this block diagram in Matlab and Simulink. Okay, we start with a blank model. Okay, once we have this untitled, go to the library. Okay, so the first one, find a FCN, which is a transfer function. Okay, just be patient. It depends on your internet connection. Okay, so this is a transfer function. Just drag this transfer function like we do previously. Okay, so it's quite slow, therefore it have a slow dynamic. Okay, again I try. Drag this. Okay, drag this transfer function. We will need two transfer function. Okay, and then go and find the source, which is the step. Okay, go and find the step. We need two step. Okay, and then we would need a PID controller. Just type PID. Search for PID. Okay, you can see here PID controller. And then, okay, it's quite slow. Okay, you would need a gain because of your transmitter and control valve have negligible dynamic, so it have only gain. Just drag a gain here, another gain to represent a sensor and transmitter. You can right click and then you can actually we can rotate it. Okay, I just want to flip the block. Okay, I just want it to be in this direction. Okay, don't forget our scope. Okay, this is a scope for us to observe the response. And then what else? We need a mat operation. Mat operation should be here. Mat operation. Okay, add. Just add. Okay, and then we would need another add. I just looking for the circle one. Oh, it is a sum. Okay, drag it. Okay, so what you need to do is you have to double click on a sum block. So you have to change the symbol from plus plus into plus minus and click OK. Okay, so the symbol is already changed. The next step is, okay, take a look on this. So the next step is you have to connect all the block. Okay, connect all the block. Okay, I don't know why there is time delay. Okay, connected all the block. Connect all the block. Okay, for here you have to drag from the tail into this line, and then the head into this line. Okay, so all the block is already connected, so your feedback loop is completed. Next, what you have to do is you have to insert the given value, which is here. The value of Kp 2.05. Okay, so just double click on this transfer function. You will see another pop-up window came out. Okay, the numerator should be 2.05. Okay, and then the denominator should be tau, should be 0.25. Should be 0.25. Click OK. Okay, you see something like this. Can enlarge it so that you can see the value of gain and the value of tau. Okay, so same goes with this transfer function. Double click, (2.05), and this one is 0.25. Click OK. Okay, and then the value of GV is equal to KV, so the value of KV is 0.75. 0.75. Just double click. Okay, and then edit this value. Enlarge it. Okay, so that you can see the value. Okay, same goes with the value of GM equal to KM. So the value is 1.5. So edit here 1.5. Click OK. Okay, so you already have your feedback control loop block diagram. Okay, which is number 1. Okay, so you already develop your feedback control loop block diagram. Okay, the next thing to do is you're going to simulate the effect of Kc, tau I, and tau d, which is in Simulink block, it is P, I, and D. Okay, for both set point change and disturbance rejection. Okay, in process control, there is always these two conditions. The first one is a set point change. The second one is a disturbance rejection. So in this figure, okay, let me erase for you first. So this section is known as disturbance rejection, and this section is known as set point change. Okay, disturbance, rejection, and set point change. Okay, let's see what happened in our Matlab. Okay, so we have the section for disturbance rejection, and there's another section for set point change. Okay, the next thing to do is you have to propose the value of your own value of Kc, tau I, and tau D. So value of P, I, and D. So in Simulink, you just double click at this PID controller. You will see a block diagram, a diagram like this. Okay, P, I, and D. This is what you're going to do. You're going to propose 3 value of P, 3 value of I, and 3 value of D. Okay, you have to propose 3 value. You can choose any value, 3 value of P, 3 value of I, and 3 value of D. Let's say you propose the first one, P, you propose, make it like this, P, the value of P, let's say you propose 1, 5, and 7. And then for the value of I, you also need to propose another 3 value. Let's say 1, 2, 3. Please choose another number than mine because I just showing you this. And then for the value of D, also another 3 value. Let's say you choose 0.5, 1, and 1.5. So at each of these settings, same values. Okay, what you need to do is you need to, let's say we choose the value of P equal to 0. Let's say we choose the value of P equal to 1. You just let's say you choose the value of P equal to 1. So you just put integral and derivative equal to 0. Click OK. Okay, so before you start to click run button, you have to check on the step, which is the step time. Okay, because of the time is 10, just put the step at 1. Okay, the initial value is 0, the final value is 1. Click OK. And then, but for this one, for another step block, we have to change the step time. Okay, maybe we can change it to 5. Okay, and then you have to click a run button. Once you click a run button, okay, it's already completed, and you just observe the response. Okay, you can see a diagram like this. Okay, I want you to try to simulate all the value of P. Okay, all the value of P, all the value of I. Make sure each of the group having different value. Okay, don't put the same value of I, the same value of P, I, D. Should make sure each group have your own value. Make sure it's not the same. Okay, so this is the response for the p equal to 1. So you have to simulate for the value of p equal to 5. Okay, let let us try it here for the value of p equal to 5. Okay, for the p equal to 5. Okay, you can just click this button directly. Okay, just observe what happened to the response. Okay, as you can see the difference. Can you differentiate between previous one and this one? The steady state achieved at different value. Okay, so in order for you to observe, to compare uh, two more than one value of p, the easiest way to do is, okay, the easiest way to do, I'm going to enlarge this. Okay, the easiest way to do is you select all this block, click Ctrl C and Ctrl V. Hold on for a second. Okay, so it's here. I'm copying, sorry. It's not my laptop that's slow, it's maybe because of my internet connection. Okay, as you can see, it is some lagging. Okay, put it here. Okay, put it here. Okay, you can use your mouse to enlarge the size. Sorry, I don't know why is that. Okay, I also don't like something like this. Okay, the next thing to do is you have to find your library and then find MUX. Okay, this is the thing. And then, okay, once you drag the MUX block, okay, you need another scope. Okay, you would need another scope here. Okay, why you need another scope here? Because we would see the the different in response for different value of p. Okay, just connected here and here. For your case, because you are doing three value of p, so make sure you duplicate all this block diagram into 3. Okay, okay, so let us change the value of p here into 1. Okay, we change it to 1. Okay, we can close this library and this p value is equal to 5. Okay, so the top one is p equal to 1, the above one, the below one is p equal to 5. Okay, click the run button. Wait for it to complete. Okay, so it's completed. Just double click on this code. You can see there is 2 lines represent 2 response, because each of these response represented different value of p. So what you need to do, you have to compare all your response based on the value of P, based on the value of I, based on the value of D that you have choose. So you have to, what you need to do is you have to compare. Okay. And that will be your discussion. Okay. For you to compare, okay, you have to calculate the value of rise time. Okay, the value of rise time, the value of settling time, the value of oscillation and period of oscillation. This is you have to calculate from the response. Okay. How to calculate this? You have to refer to, I already put a simple definition of this rise time, settling time, oscillation in this lab module. You have to go back to the above one, which is before you start the lab number 1. Okay, this is at the theory background in front section. Okay, a background theory. It is inside your lab module. Okay, you have to go to the input and response, and this is the performance characteristic, whereby how to calculate a rise time. Right, this is the value of rise time. Okay, this is the value of rise time, TR. Okay, you measure here, and the value of period of oscillation between two peaks, the distance between this peak and this peak, the settling time, which is this one. Okay, and then the overshoot, which is the value of A and the value of B. Okay, so for this response there is no overshoot, but later on when you test for different value of I, different value of uh, D, you're going to see some oscillation. Okay, so what you need to do is you have to, in your lab report, make sure you screenshot this block diagram together with the response, and then discuss in term of this term, in term of the rise time, which one have the highest, which one have the lowest, which one is higher, which one is lower. And then in term of overshoot, which one have the overshoot, which one doesn't have overshoot. Same goes with a settling time, which setting, which PID setting will give you different, will give you longer settling time, and which one giving you shorter settling time. And then for the value of P, let's say you choose the value of P is 1, 5, and 7. Okay. For the value of I, you can choose to use, you have to fix the value of P. You have to choose, you have to put it, let's say you choose the value of P equal to 5. So you just propose another 3 value of I. It could be 1, 2, 3. And then from these 3 value of I, you can choose only one for you to continue for the value of D. Okay, 0.5, 1, and 1.5. Okay, so for your simulation, you have to do, first you have to do for the value of P equal to, in that setting, okay, in the Simulink, you have to do for P equal to 1, I, and D, put it as 0 and 0. This will give you one response, and then you have to do it again. You have to duplicate the block diagram, put it P equal to 5, I equal to 0, D is equal to 0, and then for P equal to 7, I is equal to 0, D is also equal to 0. And then this will give you 3 response. So From these three response, you have to compare. These three response will give you the effect of P or the effect of KC. If KC is higher, if P is higher, what happened to the response? What happened to the rise time? What happened to the rise time? What happened to the settling time? What happened to the oscillation? What happened to the overshoot? Okay. And then you repeat the same procedure for the value of I. Let's say you choose the value of P is equal to 5. So the setting should be 5, 1, 0. This is the value of P, I, and D. Okay. And the first one and the second one should be 5, 2, 0. The third one should be 5, 3, 0. Okay. This is the effect of you will see the effect of tau I or the effect of I. Okay, what happened when I increase? What happened when I is increased? What happened to the rise time? Again, what happened to the rise time? What happened to the settling time? What happened to the overshoot? What happened to the period of oscillation? Okay. And the last one is the effect of D. The effect of D, same. Okay, let's say you choose the value of P is equal P, I, and D. Okay, we fix the value of P equal to 5, 5, 5. And then the value of I, we choose 2, 2, 2. And then you just, where is the value of D? 1 and 0.1.5. So observe the effect of D. What happened? Okay. So that would be your discussion. The effect of I, D, the effect of P, I, and D towards your response. Okay. I think that's all about the theory and how you're going to do this lab number 8. I really hope that this video will help you a lot to understand a theory behind together with how to complete this lab work. Okay. With that, thank you very much for your time. See you in class later on.